Hi everyone, welcome to AI Crack channel. This is Akash Gangwar and today we'll be studying indefinite integrals lecture 1. So indefinite integration or just integration is the reverse process of differentiation. So basically let's take an example first. So d by dx of let's say sine x, that was cos x, right? Now if I try to do integral of cos x dx, that should give me sine x because integration is the reverse process of differentiation. Now here's a caveat. Let's say if I write d by dx of sine x plus c, that would again be cos x. So our integration process should have eventually some constant over here, right? If I'm trying to do integral cos x dx equals to, then it's not just sine x, it's sine x plus c. This is called as integration constant. We'll eventually find out the value of c when we are studying different definite integration, but in case of indefinite, you have to just put the value c over here, right? Now, these are some elementary basic formula for integrals. That is nothing but considering the process of reverse of differentiation. So we know that we'll find out, we'll get the value x raised per n when we differentiate this one. So that is why x raised per n becomes this. But this is only applicable when n is not equals to 1. This is applicable for all the values of n, but not equals to -1, right? So how did we find out? We just did the reverse of differentiation over here and we found out this value. And similarly for ln x, we know that derivative of ln x is 1 by x. So 1 by x integral is ln x plus c. Similarly for e raised per x, similarly is for a raised per x, and similarly for all these examples. So these are not formulas, these are just the reverse of differentiation and nothing else. Now let us talk about theorems of integration. So the first theorem says if we have a constant k inside the integral, then we can pull out the k outside the integral. So this is same as differentiation. So basically in differentiation, what we used to do is d by dx of 2x square. That would be 2 times d by dx of x square. This was the thing we used to do in differentiation. Exactly similar is the case for integration. So we have, let's say, 2x square dx integral, that would be 2 times x square dx. Both are same, right? Similarly, we have the case for summation and subtraction. Let's say we have fx1 over here, not fx1, f1x over here plus f2x over here, and as many as function as we want dx. So what we can do, we can write it as integral f1x dx plus integral f2x dx. Similarly, we can write it for on and on for all sorts of functions. Now the third point is, if integral fx dx equals to capital Fx, then integral f of ax plus minus b dx equals to 1 by a capital F of ax plus minus b. Now let's try to understand with this with an example. So let's say we have fx equals to cos of 2x plus 3. Let's say we have this. And if we want to find out the integral of this function, so what we'll get, integral cos of 2x plus 3 dx. That would be, we know that integral of cos is sine. So we'll get sine of 2x plus 3 multiplied by the inverse of the coefficient of this one. Sorry, not inverse, reciprocal of the coefficient of x. So that would be 1 by 2 plus c. So this would be our answer. Let's say we want to calculate for sine of, let's say, 3x plus 2. In that case, if we do the integral, we'll get minus 1 by 3, minus because of the sign, minus 1 by 3 because of this coefficient, into cos x, cos of not cos x, cos of 3x plus 2 plus c. This is the integral we'll get for this one, right? So this points tries to demonstrate this particular property. Now, since we have understood the theorems of integrations, so let's look at some examples. And before looking at the examples, let's try to understand that we have understood these basic formula because we want to convert every function inside the integral to these kind of standard forms, either through rationalization or through anything, any adjustment, whatever you do to not change the function inside, and still you are able to convert the function into simpler forms or the standard forms. That is our main goal in the elementary integration. We'll look at the complex process afterwards, but as of now, our main aim is to convert the inside function into a simpler version. With that being said, let's look at the first example. Integral of 1 minus tan square x divided by 1 plus tan square x dx. Now we know that this is not a standard format and we have to eventually convert into standard format. So here our trigonometry concepts will be utilized. So basically we know that if you directly know that this is the formula of cos 2x. If you don't know that, you can actually derive it. Just convert this into sin x and cos x. So we'll be getting 1 minus sin square x divided by cos square x divided by 1 plus sin square x divided by cos square x. So this would become cos square x minus sin square x divided by cos square x divided by sin square x plus cos square x divided by cos square x. So this gets cancelled out. This is 1. So we have got cos square x minus sin square x. That is nothing but cos 2x. So we know that either through formula or through derivation, we know that this internal function is nothing but cos 2x. So we have written cos 2x dx over here. So if we try to do the elementary integration over here, we'll be getting sine 2x divided by 2 because we have got the coefficient over here. So sine 2x divided by 2 plus integration constant c. Right. Now let's look at one more example. X raised power 4 plus x square plus 1 divided by 2 times 1 plus x square integral dx. Now whenever I see 1 plus x square in the denominator in case of integration, I get the idea of tan inverse x, right? Because we have a differentiation of tan inverse x as 1 upon 1 plus x square. So whenever I see 1 plus x square in the denominator, I tend to get a feeling of tan inverse x in the answer. Just the first thought, not the final answer, just the first thought. Now let's try to proceed further. So basically, to convert this denominator into tan inverse, so basically to get a tan inverse formation over here, what I'll do, I'll try to eliminate this particular thing, this one from here. So that would give me x4 plus x square divided by 2 times 1 plus x square plus 1 divided by 2 times 1 plus x square integral dx. Because of the property, because we have studied in the second theorem that we can split the functions or we can combine the functions. So now this becomes more simpler. This would give me x square 1 plus x square in the numerator. That would give me 1 plus square dx plus this is nothing but 1 by 2 times tan inverse x plus c over here. And what this is, this gets cancelled out. This is x square by 2. For x square we have the integral 1 by 2 times 1 by 3 into x cube plus 1 by 2 tan inverse x plus c. So this is our final answer. I'm sorry for the poor handwriting, but yeah. Now let's look at one more example. 1 plus tan square x divided by 1 plus cot square x. Again we have to do the simplification over here. So if you can see, this numerator is nothing but sec square x. So this is sec square x divided by this is cosec square x dx. This eventually becomes, this is 1 by cos square, this is 1 by sin square. That actually becomes tan square x dx. Now tan square is nothing but sec square x minus 1 dx. So for sec square x we have integral as 10x, for minus 1 we have integral as minus x plus c. So this is our final answer. So basically we have to convert these into standard formats to get an answer in the elementary integration. Now let's look at one more example. Integral of 2 plus 3x square divided by x square plus 1 plus x square. Now again I'm getting 1 plus x square in the denominator. So again that kind of thought process should be there. But we have an additional x square over here. So I can do two adjustments over here. So the first one would be, let's say I add and subtract 1 in the numerator. So that will give me 1 plus 3, sorry, minus 1 plus 3 plus 3x square divided by x square 1 plus x square. Why I did that? Because that would give me, if I take 3 common from here, I'll get 1 plus x square over here and that would cancel out. So that was the first thought process. Now that would give me minus 1 divided by x square 1 plus x square plus 3 times 1 plus x square divided by x square 1 plus x square. This gets cancelled out and this becomes the standard integral. But now over here we have got one more problem over it because we don't know how to solve this one. We can definitely do this with the help of partial fractions, but that is the advanced phase. But as of now, in the elementary phase, we don't really know how to solve this one. So our this kind of adjustment was not good one. So let's try to do another adjustment. So what I can do, I'll split 3x square as 2x square and x square. So that would give me 2 plus 2x square divided by x square 1 plus x square dx plus integral of x square 1 plus x square. Now why this thought came? Because that would convert this into 2 times 1 plus x square. That would eventually cancel out this one, and over here x square gets cancelled out with this one. So that would make my life more simpler over here. So this gives me 2 times 1 plus x square divided by x square 1 plus x square dx plus this one cancels out and this becomes standard integral of tan inverse x 1 plus x square. So this cancels out over here. This is also a standard integral 2 dx divided by x square, and plus this is tan inverse x plus c. So this is how your thought process should be aligned. Now, since we have seen the elementary methods of integration, let's look at some advanced methods of integration. The first one is substitution, second one is integration by parts, and third one is partial fractions. I'll be introducing substitution in this lecture, and we'll be studying in detail about substitution in the next lecture. Now let us talk about substitution and what is the idea behind substitution and when do we need it. So let's take an example first. Let's say we have got an integral cos x ln sin x dx. Now we don't really know how to convert this into a simpler format with the help of rationalization or any other adjustment. We don't really know how to convert this into a simpler format. So basically in such a case we need substitution. So basically idea behind substitution is to convert these difficult integrals or complex integrals into simpler integrals so that we can calculate them further with the help of simpler versions or standard integrals. So let's see how do we do that. So over here, what I'll do, I'll take sin x equals to t. So if I differentiate both sides with respect to x, I'll get cos x equals to dt by dx. So basically cos x dx, if I'm cross multiplying over here, cos x dx equals to dt. So basically this gets clubbed in dt. So eventually what we got ln sin x, sorry, not ln sin x, ln t multiplied by dt. This is the final integral. Again, it's a complex one, but it's much better as compared to this one. We will have to apply by parts over here to calculate further, but it's much simpler and better as compared to this one. So this is the power of substitution. So the second most important question is what should we choose to substitute? So I'll categorize this into two broader parts. So the first one is composite functions arguments. Now what do we mean by that? Let's say we have got a function. In the previous example we saw that we have got a function like ln sin x, or let's say we have got sine of cos x or sine of anything else. So basically we have got composite functions over here, and in most of the cases the argument the argument which is there, that is used for the substitution. So for example over there we chose sin x equals to t, and in this case let's say we have again sin x multiplied by over here. So what I'll do, I'll choose cos x equals to t, and that would give me minus sin x dx equals to dt. So this gets clubbed with the dt. Now in the second category, let's say we don't have a composite function, but we do have a function which is very complicated and it's not further simplifiable. So it's not going to be simplified further and it's highly complicated. In that case, we have to choose such an argument, such a substitution that would eventually convert the function into a standard integral. We might not find that kind of integral questions in the PGDBA examination, but we'll definitely study about them. In most of the cases, you'll get these kind of substitution questions in PGDBA. Now let us look at this example, integral of cos of ln x divided by x dx. Now the first intuition over here should be to take ln x equals to t because this is the argument. And also we see that we have 1 by x dx over here. So that is the derivative of ln x. So that gives us good chances to convert this into a simpler format. So let's take ln x equals to t. So 1 by x dx would be dt, right? So basically this gets converted into dt. So we'll be getting cos of t into dt. So this became a simpler version. So from having ln in this format, this became a simpler version. So what we'll be doing over here, that would give me sin x is not sin x, sin t plus c. Now we have to put back t again over here because the actual function was in terms of x. So that would give me sine of ln x plus c. So this is our final answer. So this was just the basic illustration to see how substitution works. So today I'm pausing this lecture till here only, and from tomorrow onwards we'll be delving deep into the substitution integrals. So let's meet tomorrow. Thanks for watching.